Welcome to Unit 10 Acid Bases, Lecture C. We're going to talk about conjugate acid-base pairs today. The conjugate acid-base pairs are going to be our Bronsted-Lowry definition of acids and bases. So just to review that briefly, acids are proton donors, and in our shorthand, a proton, remember, is the same thing as a hydrogen, positive one ion. Bases are proton acceptors, so they are going to gain an H+. In order to be an acid in this Bronsted-Lowry definition with an acid-base pairs, if you're going to be an acid, your compound has to have at least one hydrogen in it that it can give away. And if it's going to be a base, it says it has to have at least one unshared pair of electrons. So remember, when we did our Lewis dot models, if I made a Lewis dot model for water, the shared pair of electrons where the hydrogen was attached to the oxygen, shared pair, dot and X, this over here, where both of those dots are from oxygen, was our unshared pair of electrons. As long as you have at least one unshared pair of electrons, you're capable of being a base. So if we add our Lewis dots model to our example here, the water is going to be acting as our acid, because when we look at what he turns into, he was H2O. On the right hand side, the closest thing to that is this OH, so he has lost one hydrogen. When the hydrogen broke off, he was positive, which means he left his electron behind, so you have this extra electron here, making your hydroxide ion -1. Our ammonia, pretend these hydrogens are lined up correctly with our Lewis dots, has one unshared pair of electrons right here. When it reacts, it goes from H3 to NH4. So he gains a proton. He has one extra hydrogen. And because what he picked up was a hydrogen +1 ion, because it's on this unshared pair of electrons, the whole polyatomic ion picks up this +1 charge. So in the forward reaction, the H2O is our acid, and the OH- is our base in the reverse. The NH3 is our base in the forward reaction, and the NH4+1 is our acid in the reverse. These Bronsted-Lowry acid-base reactions are reversible. What's an acid in the forward reaction, because it donates a proton, becomes a base in the reverse reaction because now it accepts one. What was a base in the forward reaction now becomes an acid because it donates the proton. We can look at some of our Arrhenius acids the same way, as long as we take into account the water that we're using to dissolve the acid in the first place. So if we look at the example here in your notes with water and hydrochloric acid, so I'm going to add all of our Lewis dots. Our water in the forward reaction is going to go from H2O to just H3O. Notice that your difference between the forward and reverse reaction, the pieces are always different by one hydrogen. So to go from H2 to H3, you must accept a proton, so that makes the water a base in the forward reaction. To go from H3O to H2, you have to lose one of these hydrogens, so that makes this H3O, or the hydronium ion, an acid in the reverse. If we pair up the HCl with what it turns into, which is a Cl- ion, our HCl goes from HCl to just Cl by losing the one proton, so he's a proton donor, and it is an acid in the forward reaction. The Cl- turns back into HCl by accepting one proton, so the Cl- is a base in our reverse reaction. We call these conjugate acid-base pairs. The water and the hydronium ion are our conjugate acid-base pair, and the HCl and the Cl minus are our other acid-base pair. Remember, what's an acid in the forward reaction is a base in the reverse. Because water can act as both an acid and a base, it is amphoteric, and I've just shown you two more examples where that happens. Our notes up here are really the answer to this question down here for 4. What are the conjugate acid-base pairs? It's water and the hydronium and our HCl and Cl minus. If you just have a compound itself and you want to know what the conjugate base of an acid is, remove a hydrogen. If you have a base and you want to know what the conjugate acid would be, add a hydrogen. So if we have this HNO3 and they want to know what the conjugate base is, we're going to just remove a proton and see what we get. So if we take off an H plus, we have an NO3 minus 1. Just remember to get the conjugate base, remove an H plus. To get the conjugate acid, add an H plus. And that wraps up Lecture C.